So we already talked about lots of model of computation, and we said that the two main categories are automata and grammar. And even in automata there are four main categories, and the simplest one is finite automata. And even inside finite automata, we have deterministic finite automata, non-deterministic finite automata, and some other variants. So the simplest one to start with will be deterministic finite automata. So let's start with all the rigorous definition and all the proper mathematics. So as we have already mentioned before, a finite automata is a mathematical model of a machine, and the name finite comes from the fact that the machine can be in any one of the finitely many internal configurations, which we call states. So think of any physical machine, and somehow you should be able to describe the state of the system. So just take this very non-mathematical example. So there is a simple circuit. If you push the switch, the light will be turned on. If you push the switch again, it will be turned off. Now, how will you describe this system? Okay, how to describe the system mathematically? Now, you can write all sorts of equations of physics. You can, in principle, can ask for all the information of all the subatomic particles and quarks and electrons, but that is not really required if all you are interested in is whether the bulb is on or off, right? So that means you are modeling the state of this system as just this off and on, and we give it some formal names. Say the off state is Q off and the on state is Q on. So the set of states is just this Q1 and Q off. So this is Q, and this is finite. So that is what I mean by the machine can have finitely many internal configurations or state. So here you have just these two state, right? Now this is our machine. Now what is the input to this machine? So the only way to provide input is to press this button, right? Now let me just name this action, this pushing this button once. Okay, so pushing this button once. So this whole action, let me name it by some symbol A. Okay. Now we can push it as many times as we like. So pushing it twice will be encoded by this string AA. So in general, the action of pushing the button I times, so that will be denoted by this string A concatenated I many times, A to the I, right? And not pushing the button at all, that is also an action, right? So pushing the button 0 times, so that is the empty string because it doesn't have any A, and each A stands for pressing it once. So what are the possible inputs to this machine? So these are all the AIs, including this A to the 0, right? So these are all the possible inputs. So this is the universe of all the inputs, and you can see that these are all the strings over this alphabet. Okay, so we already have an alphabet containing only this symbol A. These are strings, so we have encoded our input as strings. You remember in the proper definition of computational problem, and we needed the input set of all inputs will be set of strings over some alphabet, right? So here we have fixed our alphabet, and we consider all the strings over this alphabet as all possible inputs. And just observation that the number of states, so this is finite, this is cardinality 2, but the set of all possible inputs, that is infinite. Okay, set of all possible inputs is infinite, and that has to be the case. If you are solving a problem with your machine, it should be able to take all sorts of inputs. Now, how does this machine react to the input, right? So now if it is in this off state, and then if you press the button, so if you apply this action, so it switches to this state, right, this on state. And similarly, if it is in on state and if you apply this action, so it jumps to this state. So this system in a very abstract sense is jumping between these two states, which is triggered by this action which we encoded as some symbol A, right? So this behavior can be encoded by a function. So we call it transition function delta. And so what are the domain and range of this function? So this function needs to know the current state and the action that you are taking on this machine. So depending on that, it will give you the next state, what will happen next, right? So this is the domain, this is the range. Okay, it takes a state, it takes a symbol, and it produces another state. So this is the current state and this is the next state. Okay, and this is the current input symbol. So here we only have one symbol. So you may say that why should we even have this here? This is always going to be A, right? But later we will see that we can have different symbols. The alphabet can be anything, any finite set, right? So there should be some option to take this into account. But anyway, we can at least mathematically express the behavior as this function. Now we want to extend this transition function delta. So what is delta doing? So it's looking at the current state and just one symbol, the current symbol, and then it's producing the next state, right? So now if I ask the question, okay, the current state is given and I give you a sequence of input symbols, right? So input can consist of many symbols, as we said. So the set of inputs is this, right? So what if we push the button 3 times? So this is what we want to know, that if we start with some current state, okay, and then we apply a sequence of symbols. So a sequence of symbols is what? A string. It's a finite sequence, so it's a string. So then what will be the next state? That is what we are interested in, and that we can encode as a function delta hat. Okay, so the difference is so for delta the domain was this q times sigma, because this was just a single symbol, right? So now we are saying that we know the current state, and then we are considering a string, a sequence of symbols. So after processing all these symbols, what will be the state? So that is what this delta hat should return. And this delta hat is completely determined by delta, right? Because if you know delta and you start with, say, this state q, so this you apply, say, some symbol. Here we again have only one symbol, but let's just pretend we do not know that, so that there can be multiple symbols. So if that is the case, then so this delta will tell you what will be the next state after you have read this one symbol. So now if you are in this state, again you can apply this delta on the second input symbol. So then you get this state, and you can do this repeatedly. So if you if the string that you are considering is, say, a1, a2, a3, so you can repeatedly apply this a3, a4 with this delta. So finally you will arrive at some state which we call as this delta hat of q and w. So this w is just all these symbols. And since this has to be defined for all strings here, I mean, we should consider the empty string also, right? And the most sensible thing to define this as q itself, because this kind of is telling that if you are in current state q and if you do not process any input symbol at all, so this is empty string, that means it does not have any symbol. So if you are in current state and if you are not processing any symbol at all, then you are still in state q, right? So this is how we can properly define this thing. So this is a recursive definition. So we first define this for all q, all state q, and then for any string w and any state q and any symbol a. So this a is symbol, this w is a string, right? So that we can define as follows, that first you feed this string starting from this q, so you arrive at this state, and this is hat because this is a string. And then from this state you just take one single step which is determined by this a, and then you arrive at this state. So you see that this delta hat is completely determined once you fix this delta, this transition function. Okay. And also it's obvious that so here we can have any string because this is delta hat. So here if we just have one symbol, so that is also a string. You can treat a single symbol as string of length 1. So if we do that then this is exactly same as this delta, right? Because this is just a generalization. So this is saying that starting from q, if you accept a or process a, then what will be the next state? So this is saying that if you are in q and then if you take a sequence of symbols, then where will you land? So if you take this single symbol, so this is same, right? And that follows from this formal definition also. I mean, we do not need to resort to common sense argument. So once you rigorously define something, it follows as theorems or whatever. You can prove everything. So, and that is why this delta hat is an extension. So if you know the definition of function extension, you know, right? I mean, extension means you are enlarging the domain without changing the value for the smaller domain that you started with. But anyway, so now In the previous lectures, I mentioned about determinism and non-determinism, and I said that in deterministic automata, not just finite automata. So here we are talking about finite automata because the set of state is finite. So in any deterministic automata, if you know the current configuration, so the next configuration will be completely determined by the current input symbol. Okay. So if you know the current state, and so here configuration means state in this finite automata setting. And now if you know the symbol, then the next state is completely, it's uniquely determined. There is no this or that about this thing. So in that sense, this is a deterministic finite automata. So what will be a non-deterministic behavior? Now suppose our switch is faulty, okay, but it's not completely faulty. So so what I mean is that, say, suppose you are in on state. So if you press this switch, you always go to off state. So in that direction it works perfectly. But if it is in off state, so this is depicted by this arrow, right? So if you are in on state and if you press this button, you switch to off state. So there is no problem there. That's still deterministic. But if you are in off state, okay, if you are in off state and if you push the button, then you may or may not go to this on state, right? So you may still remain in off state. So you just push it and it doesn't switch on. So suppose your switch is faulty in this fashion. It's a very artificial example, but anyway. So that means from this current state and from the given current symbol, which is in our example is always A. So next state can be either Q off or Q on, right? It's either on or off the next state. So that means it's not uniquely defined. So we have a non-determinism here. So this is what a non-deterministic behavior can look like. So later we will study non-deterministic automata in detail. So in fact, in the current lecture we will only focus on deterministic automata, but it's helpful to always have in mind that there are other things. We are only focusing on deterministic part, and it can be non-deterministic. So now it's fine. We have a machine, and it kind of looks ridiculous to you, perhaps, to encode the action of pushing the button as symbols and multiple push as strings and all these things. But still we have some kind of machine, and we have somehow encoded that machine as some kind of graph. So you are making transitions between states and all those stuffs. But see, the thing is that we need to solve some computational problem. So that is why we are considering this models, right? If it cannot solve any computational problem, then what's the use of constructing it? So let us solve a computational problem with our example. Okay. So here is the problem. Given any natural number n, decide whether n is odd. Okay, this is a decision problem. So that means you have to make this decision for all natural numbers n, and in natural number I also include 0. So again, if you forgot the definition of computational problem, go back to those slides and just be absolutely clear about what a computational problem is. So this is our computational problem. It's a decision problem. So we have already okay. So right now, forget about the machine for the time being. So given a problem, we said that we need to encode the inputs, and then there will be a corresponding language which captures this problem, and that language, the final problem is to decide for all input strings whether that string belongs to that language or not. And that language is precisely the set of all ES instances. So how do we encode the input here? So here we are just using unary encoding. So unary encoding means n will be this natural number n will be encoded as this consecutive n many a's. Okay, so this is a string. This is a symbol. This whole thing is a string. So there is a unary encoding. So the most primitive thing, right? You draw one, say, line for 1, 2 lines for 2, 3 lines for 3. So instead of drawing lines, we are using this symbol a, right? So this is how we encode our integer. And then what will be the language? So the language will be the set of all strings for which the answer is yes. That means for which the n is odd, because this is what we are trying to solve, right? So this is our language. It's a language over this alphabet, just containing this one symbol. Now we have also used this symbol to in our machine. So in a very abstract diagram, this is what our machine looks like. It has two states, and it can switch between these two states, and the transitions are labeled by this thing. And then we have defined this problem, right? And how do we solve this problem using this machine? So this is our machine, this is our problem. How do we solve this problem using this machine? So the strategy is that you start with this Q off state. Okay, so this is the starting state, so which I have marked with this additional arrow. So this means that you start with this state. We call this starting state, and then you apply the input. So you apply the input string a to the n, right? So if your input to the problem is the natural number n, that we encode as a to the n, and that is a string. This string is an input to our this finite automata. And on this input string, what does it do? It just reads this input string one symbol at a time. It reads a n many times, and after reading each symbol, it makes the appropriate transition. So it starts here. So on reading, say, the first a, it makes this transition and goes here. Upon reading the second a, again it makes this transition and comes back here. So it does this. So it is obvious that if it has read even many a's, so then it will come back to this q of, because it started with q of. If it has read odd many a's, so then it will be in this q on state, right? So you remember that we have to have some acceptance criteria for each automata, right? So here the acceptance criteria will be that after reading all the inputs, it should be in this q on state. So this is the desired final state. Okay, so that means our machine has a final state. Now I have deliberately used the starting state and a final state. That is because this is a very specific example of DFA. We haven't even touched upon the formal definition yet. We will reach there. But even in this, okay. So now when we talk about some general DFA, so always we start from some state, so that will be a fixed state, so that will be the starting state. But there can be more than one final state. Okay, so in a so in general, it is not necessarily true that we have only one final state. So there can be more than one final state, so we should consider a set of final states. Okay, so here the set of final state is just this singleton set consisting of just this state, right? So now everything is now mathematically defined. So how are we describing our machine? So we have defined all these quantities. So we have described this finite set of states. Okay, and this has to be a non-empty finite set. Okay, then we have input alphabet. So all the inputs must be a string over this alphabet. That is what this machine is capable of processing, right? Then we have a transition function with this domain and this range, which encodes the behavior of the machine. Yeah, so here the starting state is Q of right, and we have defined a final state, but we said that we should consider the set of final state, which in this case is just a singleton set consisting of this state. So we consider the set of final states. Okay, it's a set. So all these quantities together, so they define our automata. How many of them are there? There are 5 entities. So these are sets. This is some element here. This is a subset of this. Okay, and this has the signature this, which depends on this input alphabet. So this 5 tuple, so this completely defines our machine, and with this we set up this acceptance criteria that a string, any string over our input alphabet, so it is accepted. So if and only if starting from this Q0, which is the starting state, and processing this W, you end up in some final state. Okay, so this is telling that this state that you reach after processing this W has to be a final state. So this is the set of all final state, so this has to be one of them. But in this particular example, again I am telling this repeatedly, that since it's singleton, it's means that it has to be just this thing, but in general there can be more than one final state. So this should be a proper way to express that thing. Now when we are drawing this diagram, again there are very specific rules to draw this diagram. This is called transition diagram of a DFA. So the DFA is this 5 tuple, right? There is no picture about this thing, but we can express this DFA as a directed graph. Okay, and the edges are labeled with symbols, so it's a labeled directed graph. This is known as transition diagram. And what are the vertices? So you know what a graph is, right? From this graph theory, so discrete math graph theory. So it has some vertices and some edges between vertices. So vertices are states, and edges are labeled with input symbols, which just depict the transitions between states. on this particular input symbol, right? And there will be this starting state, so which will be marked with this additional arrow, and all the final states. So here again there are only one final state, so all the final states will be marked with this double circle. Okay, so this is the convention, drawing convention. Now that was a very specific example. In general, what can be a deterministic finite automata? So it's same. So in this example, we only had some specific value for this set, and this set, and this function. So in general, DFA can is this 5 tuple, where this Q is a non-empty finite set. This is very important because we are talking about finite automata, and each element in this set will be known as a state. So this is a set of states. So again, this is a non-empty finite set, this sigma. So this we take as some alphabet, and the elements are symbols. Then we take some function which takes a state and a symbol, and then spits out another state. And then we have one state here which belongs to this set of all states, which we call starting state, and we have a subset of all these states which we call the set of final states. So any state in this subset will be called a final state. And the crucial difference between the previous example and here is that in general there can be more than one final states. Okay. And this can be any subset. I mean, this can have this Q0, this can exclude this Q0, and there is no restriction on that. And as I mentioned before, the transition diagrams, the convention for drawing transition diagram is that the vertices are states, okay, and the labeled edges, so between these two vertices, so that depicts the fact that delta of QA is P. So if you start with Q, you process input symbol A, you land in state P. Sometimes we label the edges with multiple symbols, right? So this means that for all these symbols, if you start with Q, the next state will be P. So this is true for all these symbols. So instead of drawing 3 different arrows, we just to keep the drawing simple, we label it with multiple symbols. And the starting state is marked with this extra arrow, and all the final states. Okay, again there are multiple final states, so all the final states are marked with this double set. Okay. So here is a more complicated example, right? So the previous automata, it's very simple to see that the accepted language. So again, what is the accepted language? It is the set of all strings that are accepted, right? That we defined in the previous lecture. So the accepted language for the previous example was the strings containing odd number of A's, right? So that was very simple to see. So now can you see what the language here is? I mean, can you come up with a simple description? Now, obviously, this transition function describes it in some complicated way, but can you see a simple interpretation of the language accepted by this DFA? And pause the video for a moment and try to figure out what this machine is accepting. Okay, so Anyway, so here again you see we have this 5 tuple, and here we have 4 states, all these 4 vertices, and the transition function is this. From Q0 on input 0 you go to Q2. So from Q0 on input 1, on input 0 you go to Q2. So this transition, right? So this is labeled by this 0, and similarly for all these things. And sometimes, so when we write down this function, we can write down this function as this table, obviously a tabular form. So this is known as transition table. This is a transition diagram, and this is transition table. Okay. Now in transition table, sometimes though Hopcroft-Ullman doesn't use that notation, Hopcroft-Motomani-Ullman uses this notation, that in the transition table you can have this arrow to denote that this state is a starting state, and then for each final state you can put a star. So here the starting and final states are same. Again, it has only one final state, so this is atypical. We will see examples with multiple final states, but anyway, at least here this is the state which is both the start state and a final state. Okay. So what is the language that it's accepting? So you see, you can divide this automata, say by this fictitious line, and when it starts, okay, it hasn't seen any zeros, any ones. So that means it has seen 0 number of zeros and 0 number of ones, right? So now if it sees a 1, then it will move to this side, okay? And here, now if it sees 0, say a couple of 0, okay, so say it makes this transition on a 1, and now it can see arbitrary number of zeros which it can process with this loop. Okay, so again, so after coming here, if it sees say even number of zeros, it will come back here. If it sees odd number of zeros, it will go here, right? But still it's here means it has seen only say 1 1, right? Then if it sees another 1, it will come back to this side. Okay. So either it can make the transition, make this transition on the second one, or it can make the transition here with the second one. But anyway, it will come back to this side. Okay. And it's not hard to see that this imaginary line, so it divides the machine into the states such that if the machine is in this region, that means it has so far processed only even many ones, okay, 2 ones, 4 ones, 0 ones, 6 ones. And if it is here, that means it has so far seen odd number of ones, right? And by symmetry, you can argue that you can divide this machine like this, and if the machine is in this region, that means it has seen even number of zeros, and if it is here, that means it has seen odd number of zeros. So that means it starts here, so that means it has seen even number of zeros, even number of ones, because it has seen 0 number of zeros and 0 number of ones. And after moving between all this state in a very complicated way, if it comes back here, so what is this? So this means it has seen, okay, it has so let me just make it clutterfully. So starting from here, if it comes back again here, so this quadrant means even number of zeros and even number of ones, right? So That means it accepts precisely those strings which has even number of zeros and even number of ones. That is what it means.